Derivatives with exponentials, the quotient rule, Lagrange's notation. Here we have a function, a to the power of x. When we derive that function, we get ln of a multiplied by a to the power of x. A is just a number. If you had 8 to the power of x, you would end up with ln of 8 multiplied by 8 to the power of x. That's just it. Here is Lagrange's way of doing the quotient rule, just a notation. These are the two major topics, things we'll be focusing on this tutorial. Let's just start with an example. Always easy. Okay. hx equals 10 to the power of x over x to the power of 10. We have our function fx over another function gx. If we label them as such, fx will be 10 to the power of x and gx will be x to the power of 10. When we write the derivative out, we get the derivative of fx multiplied by gx minus fx multiplied by the derivative of gx all over gx squared. Here it says we need to find the derivative of fx and the derivative of gx. The derivative of fx, f being 10 to the power of x, like I said before, you have a number to the power of x. The derivative is ln of that number multiplied by that number to the power of x. In this case it was 10 to the power of x, so it's ln 10 multiplied by 10 to the power of x. Gx is x to the power of 10, so the derivative is 10x to the power of 9. Filling this in, we get derivative of fx, ln 10 multiplied by 10 to the power of x, multiplied by gx, which is x to the power of 10, minus fx, 10 to the power of x, multiplied by the derivative of gx, which is 10x to the power of 9, all over gx squared. That'd be x to the power of 10 squared. We can, because we have a 10 to the power of x and an x to the, well, we have a 10 to the power of an x multiplied by each side, so we can factor them out, but also we have we also have an x to the power of 10 and a 10x to the power of 9. First we'll try and factor out the 10 to the power x to the power of 10 and x to the power of 9. So we'll factor out the x to the power of 9 because we have both an x to the power of 9 in these. I'll write it out and I'll stop speaking gibberish and hopefully it'll make sense. No. Okay, so here we have 10 to the power of x multiplied by x to the power of 9. in the brackets we have ln 10 multiplied by x minus 1 all over x to the power of 20. What I've done here is we have an x to the power of 10 and an x to the power of 9. Hold on, that should be a 10. We have an x to the power of 10 and an x to the power of 9. Because 9 is the one with the lowest power, we'll bring that out to the front and we'll take 9 off the 10. That's why I've just got a plain x here. And I've factored out both 10 to the power of x, that's why I have a 10 to the power of x here. And I have a minus 10 because I've factored out the x to the power of 9, which just leaves the 10. Essentially, if I was to expand these brackets and multiply 10 to the power of x and x to the power of 9 by both of these, I would get this up here. You can leave it like this if you don't understand. I'm sure whoever would be marking something like this would be fine to leave it like that. I'm just going further. And I've got x to the power of 20 because when you expand x to the power of 10 and you multiply that together, you end up with x to the power of 20. So now I'm going to cancel off the 20, cancel off the x to the power of 9, and get 11. That way my derivative, I'll rewrite it on a new page. My derivative, simplified, will look like 10 to the power of x, bracket ln 10 minus x multiplied by x minus 10 all over x to the power of 11. Let's do another example. Next one will be a bit easier. Here we have hx, our function, equals e to the power of x over 7 to the power of x. We have our function over another function. We'll label them as such. fx we'll label as ex because they're both on top, and we'll label gx as 7x because they're both on the bottom. Doesn't affect the equation at all, it's just labeling them. The derivative of hx equals f dash x multiplied by gx minus fx multiplied by g dash of x all over gx squared. We need to find the derivative of fx and the derivative of gx. The derivative of e to the power of x is just e to the power of x, and the derivative of gx is ln 7 multiplied by 7 to the power of x. That is because a number to the power of x is when you derive it, you get the natural logarithm of that number multiplied by that number to the power of x. In this case, it's 7 to the power of x, so it's ln 7 multiplied by 7 to the power of x. The derivative of hx, we'll fill this in. Derivative of fx, e to the power of x, multiplied by gx, 7x, minus fx, e to the power of x, multiplied by the derivative of gx, which is ln 7 multiplied by 7 to the power of x, all over gx squared, 7x squared. As you can see here, we have both an e to the power of x and a 7 to the power of x multiplied on either side of the minus sign. Therefore, we can factor it out. I have ex 7x, or e to the power of x multiplied by 7 to the power of x, bracket 1 minus ln 7 over 7 to the power of x squared. We can cancel off the square to get rid of the one on the top. And if I rewrite this, we have e to the power of x 1 minus ln 7 all over 7x. And that's there is the first derivative of that up here. We'll do a third and final example. Say we have hx equals cotangent x over 21 to the power of x. We have our function over another function. We'll label them as such. fx on top we'll label as cotangent of x because that's on top as well, and we'll label the gx as 21x because they're both on the bottom. The equation is f dash x multiplied by gx minus fx multiplied by g dash of x all over gx squared. We need to find the derivative of f and the derivative of g in order to complete this. The derivative of cotangent of x is negative cosec squared of x, and the derivative of 21 to the power of x is ln 21 multiplied by 21 to the power of x. Don't freak out with this up here. This here is just a standard rule. Cot x equals negative cosec squared of x. And just like before with this, 21 to the power of x, a number to the power of x, we have ln, that number multiplied by that number to the power of x. If we fill this in, derivative of fx, negative cosec squared of x multiplied by gx 21x minus fx cot x multiplied by the derivative of gx ln 21 multiplied by 21 to the power of x all over gx squared, gx being 21x squared. And go a little further. Sure, whoever's marking would be happy if you left it there. I'm only going to go a bit further because I want to show you what happens when you go a bit further. Just a little bit, obviously, but we have a 21 to the power of x on either side of the minus sign, so we can factor it out. Negative cosec squared x I'll bugger that up, sorry. 21 to the power of x negative cosec squared x minus cotangent of x ln 21 over 21 to the power of x squared. We have 2 on the bottom and 1 up the top. We take 1 off the bottom and we take 1 off the top. So what we're left with is negative cosec squared of x minus cotangent of x ln 21 all over 21 to the power of x. And that up here is the first derivative of that here. Thanks for watching. I hope this video helped.